Really nothing much to say about the announcement. I think just remember, guys, if you haven't submitted your lab number 3, as I mentioned on Tuesday, there's a grace period. Make sure tomorrow, Friday, by 12 noon, not midnight, noon. Right? Make sure you don't miss the deadline. And then for your programming test number 2, that's going to occur next Tuesday during the lecture time. And that one there, I already gave you guys the guide and also the practice question. You can look at them, so that one can give you some idea about what the format could be. In terms of the level of difficulty, as I mentioned last time, it would be about the first year, for example, EECS. Either you took 1021 or 1022, around the first year. But I would say the problems you will be given on Tuesday will be harder than the first test. So you want to get prepared. But they were still at the same level around this first year. So your best bet, you can maybe try to find out any example problems you used to solve at the first year in the lab, in the extra practice, or maybe in the programming test. So I think that could help if you try. Okay, do you guys have any questions? Jora? Yeah. Yeah, absolutely. I mean, I think, for lab submission policy, as long as you submit your best attempt, you get full marks. No question about it. Huh? Well, that's okay. As long as you submit something, that's a policy, right? But I would say for the actual programming test, we're going to see if you really have done something. Well, of course, for programming test 2, we don't test you on lab 3. Yeah, but of course, make sure you really understand the stuff before the actual assessment, right? That's my advice.
Can I double check that the assertions we're writing for lab 3, they won't necessarily all pass because of the implementation of
right. I think somehow you can even make yourself a table. I can mention about the table maybe on Thursday in the last class. Make a table to say, okay, for each of the 4 versions, you basically check both the safety and the liveness. What's going to be the check, cross, something like that. And we'll talk about it on Thursday. Okay. All right, guys, for today, I can tell you what my intention is. We got today and also next Thursday to cover more material. But I will try to say today, I will go over all the more technical mathematical stuff. And so we can finish off, hopefully, all the definition. If not, maybe 90% of them. So next Thursday, it will be more like just to give you some more examples. So before that, you can feel free to study already, for your exam if you want to. Because our exam will start pretty soon after the study day, right? But we'll talk about also your review session for you guys. So I think we can talk about next Thursday. We can see which day you guys are mostly free. And then we can hold a review session. Okay, that's something to be discussed later. All right, so this is, let's do a very quick recap so we can continue from where we were. So last time we talked about correctness, which is, again, relative to the pre and post condition that you're given for your algorithm. Specifically for our purpose, we're going to assume once you specify your implementation and post condition, they are rather fixed. And we want to see what will be the appropriate precondition accordingly. That's something called weakest precondition, which we'll start talking about for sure today. That'll be the first thing. And we'll talk about partial correctness, which means assuming that things terminate if the post condition can be satisfied. And also if you add the termination to the partial correctness, you got total correctness. That's the definition. Okay? Just don't forget. And let me see what else. And we'll talk about Hoare triple. Okay, so this will be a very important thing to recall before we get on to the lecture today. You always have this particular syntax. You got curly brackets, another curly brackets pair over here. So here you put some Boolean predicate. Here you put another Boolean predicate, a single one for each. This one here will be the precondition you specify for the algorithm. This will be the post condition specified for the algorithm. And the S over here stands for programming statement. That will be the entire code for your algorithm. okay, which can be arbitrarily complicated. And what we said last time, the informal meaning is starting with a state satisfying the precondition Q, if you try to execute the statement for your algorithm, it's going to terminate in a state that will satisfy postcondition R. It's an informal interpretation, but it's fairly accurate. But we want to know how we can formulate this notion here into two parts. One is about termination. The other part is about the partial correctness. That's what we'll do today. Okay? And one more thing to remember. Whenever you see a Hoare triple over here, always remember, itself is just a predicate that can be reduced into. And for that predicate, you can either prove it as a theorem or disprove it. Okay? Let me just say one more thing very quickly. So that one there is going to summarize the workflow for today, okay, before I get to weakest precondition. So let's say you're given some, let's say, algorithm, and then it has the precondition, it has the postcondition, and then it has the implementation. And the acronym we use, Q, R, and S. Let's say this is what you got in your TLA plus module. Okay? Always given this, I want to know whether or not my algorithm is provably correct with respect to its specification. So what I will do is I'm first going to formulate it into a Hoare triple. And that one is going to look like something like this. So syntax over here, and then Q, put here, R, put it here, and S, put it here. That's the first step, just to do the syntax. And then the second step is try to prove whether or not this Hoare triple is a theorem. If you're able to prove it, let's say it is proved, or say provable. So this suggests the original algorithm over here is correct. Otherwise, if it is unprovable, it is incorrect. So this is a very important workflow to understand. Otherwise, you might just get lost today. What's really missing from last time is how do we then turn this into a predicate that we are familiar with? Okay, that's something we're going to talk about right away. Okay. So guys, any question about the flow? Yes.
Does proving or disproving a Hoare triple tell us whether or not the algorithm is entirely correct or partially correct? Is there a way to know?
Yes, because the way we're going to formulate proof obligation, well, put it this way. You only worry about termination when you have a loop. If you only got if conditional, variable assignment, conditionals, you don't worry about termination. It's guaranteed. Let's say you do have a loop. In that case, you will have several Hoare triple that you have to prove separately. Once you have discharged all of them, it's guaranteed you got total correctness. Okay. So what Patrick was asking was about provable here. Definitely, we got different proof obligation for partial correctness and termination. All right, so that's something hopefully we'll touch upon after the break. Before the break, let's focus more on the weakest precondition, which I'll tell you what it is right now. Okay, let's now move back to the slide, and that's pretty much the flow you want to remember, and we're going to follow this particular flow. And what we're going to address right now is how can this guy here syntactically be turned into a predicate? That's what we're going to say now. How to transform a Hoare triple into a predicate. Okay, that's what we're going to talk about now. If you look at the slides, okay, that's what we said last time. Okay, start with this. Hoare triple here, by definition, it's this particular implication. Okay, let's now understand what's really here. Okay, I'll move it here. And for now, don't worry about this just yet, for now, okay? This is a Hoare triple. Let's say this part here. This is the Hoare triple. Hoare triple, which is somehow transformed from some source program, right? That's something we said. And what is this exactly? Let's try to understand each component in this particular predicate. Oh, number one, are you convinced this is actually a predicate? Huh? Well, that's true. But since we see implication here, so it gotta be something that makes sense. But I agree, we don't know what this is just yet. Assuming that, presumably, for this implication to make sense, there's gotta be a Boolean. Yeah, okay, that's what we agree. Let's now take a look. Again, please ignore this diagram just for now, okay? Let's decompose one by one. Number one, okay, just for reminder, is an implication. And this guy here is the precondition of your algorithm. And before I even explain what WP is, if I say the green one implies the purple one, what am I trying to express? But this was WP, right? So let's be a little bit more abstract. Okay, let me be more focused. If I say the green one implies the purple one, am I trying to express something should be stronger and something should be weaker? That's what I'm asking. Ellie? The purple one is true. So which one's stronger? Yeah, because Q is the left-hand side, right? Q should be stronger than this, okay? So let's understand very, very carefully this one here. So what we are trying to say over here is we are trying to express the following. Q, the precondition of the algorithm, is stronger than the WP, which I haven't yet explained, but I don't need to just yet. Are we okay with this? Okay. And let me say one more thing. The implication will fail to hold if the Q is weaker than the WP. Because I'm basically trying to express that it must be stronger than or equal to. But if it is weaker than, then it fails to hold. Okay? All right. And let's now talk about the WP. Okay? Let's look at the WP here. Let me write it again. WP, S, and then R. Okay? So the R over here is the post condition for your algorithm. And the S over here is the implementation. Oh, by the way, some happen to be the same. Implementation versus implication, right? Different words. Okay. This guy here tells you, in order for this particular implementation to really establish a resulting post condition, what should be the weakest state for you to start with? Okay, I'll write it down first, and then we'll discuss. And then we need the diagram. Okay. The weakest starting state space for implementation S to start and terminates. I shouldn't say terminate because it's kind of separate, but let's say this. To start and reach. I like the word. Start and reach. Yeah, reach is okay. It's vague enough. That's good. Reach a states satisfying R. Okay, I want you to really pay attention to this keyword, weakest. What does weakest really mean? That means anything that's weaker than that is no guarantee for the statement to terminate or to reach that particular postcondition. Let's visualize this, okay? Whenever you talk about weakest precondition, you need two. Let's think about it's more like a method or function, which will take two inputs, the implementation and the postcondition. That's why we said in the very beginning, in this particular lecture, we're going to assume the postcondition and the implementation are always fixed, because in this way, we can calculate the WP. And then the calculated WP can be used to compare with what you have for your existing precondition. Just remember that point. Let me go back. Okay, so now let's talk about visualizing this. Imagine that we have some precondition for which we want to start with a state. Let's say starting from this particular precondition, we want to execute some statements which will transform us to another state. We want to make sure that particular state is going to satisfy the postcondition. That's our intention. In order to make sure this particular definition for the algorithm is actually correct, we have to make sure the starting state over here is no weaker than the weakest precondition that we can calculate. Okay? Okay, so this one here is saying this. When we have the Q over here, you can think about the Q over here is the actual precondition. Okay? The actual precondition is no weaker than the weakest precondition for S to establish R. Okay? I haven't talked about how WP should be calculated yet. For now, understand it as more like a visual way, intuitive way. Somehow we can calculate the WP, and once you have calculated, you have to make sure your precondition should be stronger than that, or at most equal to. Cannot be weaker. Let me show you one counter example. Okay, I'm just going to copy this diagram here and show you some diagram. Okay, let's say this. Okay, let me just wipe it out. Okay, let's see this. Okay, so let's now say this. If I turn them around, let's say this is, sorry, I'll set it up. Just bear with me. Okay, let's say for some reason, let's say this is the WP for the implementation to establish the postcondition R. So this is postcondition R, okay? And this is your precondition. So what's the difference now? I kind of make the precondition itself weaker than the weakest precondition. Because it's already the weakest, anything that's weaker than that is inappropriate, okay? If you compare this part over here, in this case, the actual precondition is stronger than the weakest precondition, so that's okay. However, if your precondition is actually weaker than the weakest precondition, it is inappropriate. Especially, let me use your states to show to you. If you look at this as one state, starting from this state, which satisfies the algorithm's precondition. Because you can see this particular state is a member of the queue. Will not result in a state satisfying the postcondition R. Because in order to really result in a state satisfying R, it must start with the weakest precondition. It must be. Okay? So that means this particular one here, if you try to say, I want to execute S, it's going to go somewhere outside the postcondition. So it's not going to satisfy it. So in this case, we don't have any, the program is actually not correct. Reach or results in, so just, that's okay, as long as we don't really mention terminate, that's fine, okay. Now, let me say one more thing and then I'll take question, okay. So this is about incorrect program. Okay, over here. And this one here is about correct program. I'll take question first and then see to see if you guys need any additional details. Question? Go ahead. Weakest precondition.
Yeah, would that basically encapsulate like the largest possible state space that S can go into?
It will basically, yeah, the weakest precondition accommodates for the largest possible input values that can start your implementation with. And once you start your implementation from there, the weakest precondition, it guarantees you're going to reach the postcondition. Because the way you're going to calculate the WP is going to be based on exactly this and this, which we'll show to you, right? So this one here is really, this one here, printed the wrong thing. This WP here, this WP over here is calculated based exactly on S and R. Calculated based on S and R. Does that kind of answer your question? Or you want to ask some follow-up? S and R, both. No, this is the R, the postcondition we want to establish at the end. Yes. Think about when your algorithm somehow terminates or somehow, let's say it terminates, okay? At some point, when your algorithm finishes, you want to make sure the resulting state will satisfy the postcondition. And given this, our goal, and given this is how we reach the goal, given these two, what should be the largest possible set of input values that can guarantee such establishment? That's what the WP is about, conceptually. So now, given that WP is this hypothetical set over here, if your actual precondition is a subset of that, that's good. Because anything you start with here is still within the WP. On the other hand, if your actual precondition goes like this, it's actually weaker than the weakest precondition. In that way, for example, this state over here does belong to Q, which means the user's input will be acceptable. You can actually invoke the statement of your algorithm. In that way, because it's outside the WP, it will not end up in a state that's going to satisfy R. So that's why it's incorrect. All right, so guys, that's a very important visual intuition you want to get. Right? Everything we're going to do the calculation is going to be based on this insight. Okay? Now, what I haven't really told you guys just yet is about what S can be, which can be variable assignments, can be conditionals, can be sequential composition, like a semicolon, and also loops. And R here can just be any arbitrary assertion. Okay? And how do we calculate it systematically? That's something we'll have to do. All right, any more questions before I move on about this? Okay, think about it. You can always ask. Okay, so WP over here. And if you're able to prove this one here, that means your original program is correct. Otherwise, if you cannot prove it, in which case you might have to find some counterexample. In that way, the original program is not correct. Yeah.
So this implication is not like a traditional implication?
It is, indeed.
But then how does Q have a truth value? Like the precondition itself could be like a very, very weak precondition, right? Pretend like false, right? False is the
Very strong postcondition, very strong precondition.
So let's say it's very weak, right?
True, let's say.
Oh, never mind. Makes sense. I was thinking
Think about it. That's okay. How about let me follow up a little bit with Patrick's point. Okay, guys? Let me ask you this. What would be the precondition that's guaranteed to be always stronger than any weakest precondition you can ever calculate? False. So that means if you simply make your precondition false, it can make your program correct trivially. Yes, but is it really useful? Not really, because that means nothing can be accepted by the user, right? So let me add a remark. I think that's set somewhere in the slides. So since we got this particular implication over here, again, if Q is simply just false. Oh, thank you. Thank you so much. Thank you. So what I'm talking about is over here, implication. Okay? I'm saying that by the definition for implication, it's just the logical implication we've been talking about. If the Q is simply false, program is trivially correct. But it may not be very useful. That's a problem. Yes?
Considering that you have a range of acceptable values, does that mean you have to check for every value, the implication?
Not really, because usually, okay, remember this is actually like a predicate, right? So what we're going to see, the way we're going to do it is by doing the kind of proof that you guys did in 1090. But I will show it to you what you can do. There's going to be some equational style proof we're going to do. Sure. Precondition.
It's always one of the preconditions that we have established, right? Or is it just from the set of all possible preconditions that could be?
Sorry, can you say that again? I don't quite follow.
Like the weakest precondition that we have is always going to be an element of all the, like, of the preconditions we've established, or is it the set of all possible preconditions we've had?
No. So the weakest precondition here is more like a hypothetical set over here to say if you actually want to have a precondition for your algorithm that's going to guarantee program correctness, then this guy here, the green one, got to be a subset or stronger than the actual weakest precondition. So WP, Q, and R, all these three are simply predicates, like a Boolean predicates. And S over here is like a programming statement, like in Pascal. Yeah. Okay, think about it. It's still new, so that's why I would like to go over as many definitions as possible today, so you guys can still take some time to digest. It takes some time. Okay, not too long, but it takes some time. Okay, and can the S be over here, programming statement, can be assignment, can be alternation, if and else, conditionals. It can be sequential compositions, it can be loops. Okay, while loop, specifically. And now we're going to see how to calculate WP. So what we talk about so far is just conceptual about WP. Now we're going to be very specific about, given some implementation and given some post-condition, given these two, how do we calculate WP to result in a predicate? That's what we're going to see. Okay? And so what I will do is, I'm going to go to, just a little bit background. So this has to do with what we learned in 3342. Not very heavy, a little bit recall. Basically, think about an algorithm is more like doing a transition between the pre and post states, right? Before and after, basically. Okay? So in the post condition, over here, let me give you one example. If you take a look at this particular post condition, okay, we say B equals B0 minus A. Okay. This is relevant to what you learned in the previous course, but not exactly the same syntax. Let me copy that and then I'll talk about it. B, 0 larger than A, and then B minus A, and then, okay, there we go. Okay, let's say that's what we have, right? Let's look at what we know pretty well. This is an implementation, right? B is assigned to B minus A, pretty easy. And this one over here, whenever you see any 0 subscript, this means a pre-state value of B. Well, think about the value of B at the beginning of the algorithm, right before it starts executing. Yeah, I'll get to you. Just give me one moment. Of B at the beginning of the algorithm. Yes, question? Yes, indeed. So what you guys learned back in 3342. In 3342, let's say for the same, we have B and also B prime, right? So B here will be the pre-states. And B prime will be the post-states, indeed. The same idea. However, syntactically, you will see later on it's easier for us to really use the B and B0 to actually do the manipulation. It's just easier, less likely to get confused. You will see how. Okay? So for this course, let's say 4315, we're going to use B0 and B. So B0 here is going to be the pre-states. And B here is going to be the post-states. It could be very confusing at first, but once we start manipulating the WP, you will see that it's actually more straightforward to do in this way, rather than using the prime. A very quick look ahead. If you look at this particular guy here, right? If you look at the B here, on the left-hand side, B here is like the post-states, right? On the right-hand side, if you got B over here, well, typically in the implementation, we don't really have any 0. So it depends on the context, but in this way, it just refers to B0. Okay, we'll get to some example later. Okay, so this is the post condition you want to get used to. Okay, this one here is to say the post state value of B equals the pre-state value of B minus A. Okay, that's what it means. Okay, once we start doing some example, it will just make sense. For now, I just want to clarify some notation. One more thing to say. Usually, in the precondition, the subscript 0 over here is omitted. Because in the precondition, everything is pre-states. There's no point to really emphasize that. On the other hand, when you talk about a post-condition, very, very often, more often than anything, you are going to relate the post-state and pre-state value together. Okay? That's something you want to remember. That's basically what's said in the slides. Right? Okay? All right. All right, the first one. We're going to learn about WP rule for 4 things. We start with assignments, and then we do conditionals, and then we do sequential composition. And then we take a short break. And then we get to the loops. Yeah, loops will be the 4th one. That one is actually much more complicated. Okay, okay, let's now take a look at the assignments. Okay, what will be the definition for WP? Okay, so let me switch there. The first one here usually is the most unintuitive. Well, it's not too bad. That might take a little bit longer. But once we get to, think about this as more like a base case for WP calculation. This is like a base case for WP calculation. Once we get to other cases like alternation, conditionals, loops, and also sequential composition, they are like recursive cases. Okay? Let's understand the base case first. Let's understand in 2 ways. WP, remember the syntax. This guy over here is the implementation, like the S that we saw earlier. If you remember, over here, that's the S. Okay, over here. And then we also got a post condition. And that one there is the R. So what it is saying, in order for me to achieve a post condition R, any arbitrary predicates, by doing a single assignment, what should be the weakest precondition for me to start with? Okay, let me write down. To achieve the postcondition are via a variable assignments. What is the weakest precondition to start? That's basically what it is saying informally. Before we get to the formal definition, okay, let's see one example. Once you can get this one through, convince yourself, that's good. Let's say very simple postcondition. Let's say we want to establish x being positive. That's the postcondition. Right? We start with the postcondition. We start with what we want to achieve. And then the way to achieve it is by executing an increments on the variable. This will be the implementation. Okay? Now, if I know I want to increment my x by 1, what I want to achieve upon the termination is to establish x being positive. Now, what should be the weakest precondition? What should be the set of all possible starting states that will guarantee me after executing this, I'm going to get this? That's the way to think about it. You can just tell me the answer first, but we have to also understand how to really calculate it systematically. Thomas first. Oh. X greater than or equal to 0? If you say, okay, you're saying x greater than or equal to 0, think about what's going to happen. If you say x greater than or equal to 0 plus 1, it's going to be greater than or equal to 1. Which, does it work? Seem to work? Okay. Patrick, you want to say anything? What do you agree? X plus 1 greater than 0, that's another way, yes? Yeah. Yeah, basically, yes. Okay, let's now see how we can calculate it, okay? Basically, you're going to take the post condition here. This, okay, think about this. This x over, oh, it's really important. The x over here is the post state value. Let me use a different color. This x over here is the post state value. So the way we define this particular post condition is by using the post state value of x. And this assignment here tells us this is how we can define the post state value, right? This assignment here is telling us on the left-hand side, this defines what the post value should be. And the x plus 1 over here is using the pre-state value. Think about x. Well, you know the assignment pretty well. So if I want to update x, I want to use its current value plus 1, right? Now, the WP over here itself is a precondition. So that means everything should be defined in terms of the pre-state value. It is a precondition. That means all values are pre-states. So what we do now is, let's now do the final calculation. This guy here tells us x larger than 0. This is the post condition. And then we know by this particular definition here, it tells us the way to execute this assignment over here is by replacing the post state value by the pre-state value plus 1, right? Once you do the replacement, this tells you if I can be sure the pre-state value plus 1 is larger than 0. In that way, by doing this calculation here, it's guaranteed the post state value here, which is this, is going to be larger than 0. Let me say that again. I know that the assignment here, the implementation, is going to replace the post state value by this guy over here. So in order for this one to be satisfied, I can simply transform it into a pre-state version, in which case I just replace x by x0 plus 1, which is by definition over here. Okay, think about this base case a little bit more. Okay, that's really important. So the final answer you will see on the slides tells you this. Whenever you want to calculate what's the weakest precondition for some variable assignment to establish R, you basically take the same predicate, like over here, and then replace every occurrence of the post-state value, like x over here, by the corresponding pre-state definition, which is x0 plus 1. Okay, that's what you will get. Okay, I'll take question, and then, so the final post-condition, let's say WP for x plus 1, and then x larger than 0. Finally, we're going to get x0 plus 1 larger than 0. That's the final answer. And this one here corresponds to the implementation that we have over here. Patrick.
Examples that the post-condition value is always referencing the precondition.
Very often, very often.
So in the case where that's not the case, like if the post-condition value is something trivial, like post-condition value of x is just set to 1.
Okay.
I know the formula still works, but the reasoning is slightly different because I wouldn't say 1 is like a precondition value.
No, let's say this.
It's not like exactly a pre-state value.
Let's get to that maybe a little bit later. We might see some special case like that. Okay. So Patrick's question was, what if the post-condition itself has nothing to do with the post-state value? Oh, sorry, nothing to do with the pre-state value. You simply say, maybe x will just be equal to, did you say x just equal to some constant?
I meant the statement. Like if the statement was just assign the post-state value of x to be 1.
Mm-hmm. X equals 1. We do have something like that. How about we get there when we?
On the statement in the program.
Oh, just assign that to be. Oh.
Yeah, because I noticed that all the assignments were doing reference the pre-state, but there are cases where you may want to assign like a constant value.
Okay. Let's say this. If I say, okay, let's do this one right away. 23. Okay. Let's say x equals 46. Okay. Guys, what's this? Okay, this is valid. This is an implementation. This is a post-condition, right? So I'm asking, from what state do I start that's going to guarantee me if I try to reassign my x into 23, I'm going to establish a post-condition that's x equal to 46. False. That means there's no way. Okay? Yeah. So this one here, by calculation, so you're going to say WP rule for assignments, which is going to be x equal 46, the post-condition, and then you're going to replace every occurrence of x by 23. In that way, simplify it, you're going to get 23 equals 46, which will be false. So if the weakest precondition happens to be false, that means there's no acceptable input value that will guarantee this implementation to establish that post-condition. No, this one is not. No, this is not correct. I'll tell you why. Okay. No. Oh. No. We're gonna get there. We're gonna get there. Yeah. You guys ask good question, but one at a time. Okay. Okay. Otherwise, I will just forget to respond to some of them. They are all good points. Okay. Number one. Starting from no states. Okay. How about let me phrase it a little bit more intuitively. No input values, no acceptable input value. No acceptable input values can guarantee that x assigned 23 will establish 46. Okay, that's what we start with first. And now in this case, is it ever possible to have a correct program accordingly? No. No. It will be correct if you can have something that's actually, well, the program will only be correct if the precondition also happen to be false.
Yeah,
That's the only way,
what I'm
yes.
saying. So
Mhm.
and if you have a correct program, if you,
Well, let me write down first, okay? Okay, according to this, okay, so far this is good. And then the only way to have a correct program is this. I'm just going to give you a false precondition. And then I'm going to get x assigned 23, and then x equals 46. That's the only way. Because this is Q, right? The false will just implies the weakest precondition also happen to be false. Right? This is going to be true. That's the only way. Now think about what this program is doing. In some ways correct because it simply wouldn't allow you to even start this because it knows you can never establish the postcondition. So in some ways correct, it makes sense, but it's not useful at all. It just wouldn't allow you to start. Ellie.
So false is the strongest precondition, right? And so, you know, the weakest precondition is a subset of false, which in instance there is really nothing.
Just one minor detail. So you're right, false is the strongest precondition you can ever put. That's true. So that means if you put the strongest precondition, it's guaranteed to give you a correct program because it's a subset of the weakest precondition.
Okay, so this weakest precondition has to be a subset of the precondition.
No, the other way. The precondition must be a subset of the weakest precondition.
Okay, yeah, that's right. And okay, what I'm trying to get at is since it has to be a subset of the weakest precondition, there's nothing that will satisfy that, so it would be an empty set.
Yes, that's correct. That's correct. All right, guys, any question? We can do one more example, okay?
can you specify like ignoring the trivial like correctness? Like
Sorry, say it again. I don't quite
in
catch.
a scenario like this, would you specify that we should ignore this like case where the algorithm never runs?
Well, I think, this, I would say getting a WP that's actually false tells you that your implementation and the postcondition combination somehow may be inaccurate. Because that tells you the implementation there's no way for that to satisfy. So in this way, rather than having a precondition false, you may want to fix your statements. Yeah. Okay, that's good. Oh, one more insight. Okay. Okay. Okay, and then in this case, you're better off. You are better off just fixing S or R, right? The implementation or the postcondition. That'll be better. All right, let's do one more example. One more. Okay, this one here. What is the weakest precondition for, there's something pretty much like what we did. Similar, okay, but let's give it a try. So we want to calculate the weakest precondition, right? And then implementation is we're going to increment x. And we want to make sure the post-state value of x is larger than the pre-state value of x. Sounds pretty trivial, right? So now this is kind of the opposite to what we just discussed. In order to establish this by this, the WP will just be false because there's no way it's going to be established. On the other hand, what about this one here? If I simply increment my x over here, it's a guarantee I will always get the post-state value x larger than the pre-state value x. Well, sounds like pretty straightforward, right? In that way, what would you anticipate to be the weakest precondition? True, yes. When the weakest precondition is actually true, that tells you doesn't matter what input value you pass, it will just work. Okay, let's do this very quickly. Okay, and then I think I will take a short break, and then we can cover a little bit more. Okay. Okay, so for this one here, so we want to calculate the WP for x plus 1 to establish x strictly larger than x0. Okay, so now equal to, and then we're going to put some justification. So we're going to say WP rule of assignments. And then we're going to say x larger than x0. So this is the postcondition. And then we're going to do the replacement. You can think about this one here is the E. If you look at the assignment rule, it should be E. Okay? And that should be the x is assigned to x plus 1. Okay, like that. All right, so just do the substitution. You're going to get x plus 1. But to make it clearer, whenever you got pre-state value, you can put a 0 over here. All right, you can say x0 plus 1 larger than x0. And you can simplify it, cancel out both ends. You get 1 larger than 0, which is always true. So we just got another extreme case for the weakest precondition. That means doesn't matter what input you give to the program, it will just guarantee. And also, any precondition you put for your program is just going to work, because any precondition is going to be stronger than true. Okay? Consequence is any precondition will be correct, because anything implies true. Okay? Okay, let's now, and how about this one here? I'll take that, give you as an exercise. Very easy. You want to just calculate in your mind what should be the weakest precondition for this. X equals 22, agree? Basically replace the x over here by x plus 1. And then you get x equals 22. Okay, I'll put as exercise. You also see the solution on the slides. Okay? If you're not too sure, do the exercise to find out. Pretty trivial. Okay, let's revisit the two programs we have very quickly, and then we can take a short break. Okay? Oh, one more thing here. And so this is to say, okay, I'll show it to you. Let's go back to this original one. This one is how we calculate WP. Let's say if you have Q, and then you have R, and then you have X is assigned to some expression. Let's say this is the program you're given. For my particular program, I have the precondition Q, I have the postcondition R, and there's a single line of implementation. So now, how do I formulate a predicate for me to discharge to show that the program is correct? Patrick, I'll let you go.
So the first step I would do is write the Hoare triple as Q implies weakest predicate X assigned to E, or E assigned to X, and then the postcondition. And I would use the definition of weakest predicate.
Weakest precondition.
Oh, yeah.
And that one would be just R with every occurrence of X replaced by E.
Yeah.
Exactly. All right, so what I just did was to make some connection to what we knew before. We talked about how you can calculate WP for a single assignment. So this is this part here that we learned. But don't lose the big picture. Given this as the implementation and the corresponding specification, this will be the predicate you have to prove to show the program being correct. Okay? Okay. And very quickly, a few more slides, and we'll definitely take a short break. And that's the exercise I gave to you. That's what we just did. That's another exercise you can try. Okay, so let's revisit very quickly. Remember from Tuesday, we look at this program and this program. So now we can Now try to link them to what we just learned, and then we take a short break. Okay? Think about what's happening here. This guy here is the Q. This is the R. And this is the implementation. So if I write it down, it's going to be I larger than 3, I plus 9, and then I larger than 13. In order to prove that being correct, if and only if, it should be the Q implies the WP for this to establish, right? And let's calculate just in our mind. What would this be? You basically just replace the I over here by I plus 9, which would be equivalent to I larger than, move 9 to here, 4, right? So the weakest precondition for this implementation to establish this would be I larger than 4. All you got to check if your existing precondition is stronger than that. Is it? Not really. You can easily determine whether or not this guy over here implies that one. It does not. Okay? Let's fill it in, and then we'll do one more. Okay, so this will be I larger than 4, and this will be I larger than 3. Apparently, you can see the value that belongs to here will be 4. So 4 is going to be a state that's going to execute this statement here. It's not going to satisfy the post condition, right? That's what we saw last time. Okay. One more example, and then we'll take a break. And given the same implementation and post condition the same, we already know the WP of this to establish this would just be equal to I larger than 4. So what we want to argue is whether or not I larger than 5 implies I larger than 4. Indeed, right? So this is how we prove it. Okay? So think about what happens here. So I larger than 5 is the precondition, and WP is I larger than 4. And this relation does hold, so that's okay. Okay. So now we finished discussing the very basic rule about WP. After the break, we'll see how we do conditionals and sequential composition. We'll finish that at least today. And hopefully I can cover a little bit about loop. Okay. Ask any question before we take a break. Jora. Yes, that'll be acceptable. I would say, of course, if you're only to argue this is quite trivial, right? You can easily do that, yes. Or you can just disprove it by giving some counterexample like this. I think what we're going to see later will be something that's more sophisticated, in which case you got to do some justification that's deeper. Okay, so let's now take a very brief 2 minutes. And why don't we take attendance for the last time? Okay, I think for Thursday will be the last class, so I don't think we want to take it just for today, last time. All right. Okay, just get your device ready, and then let's take attendance. Oh, sorry. There we go. Start a class. The poll. All right, you can now check in. Oh, where's Chidalu? He's not here today? Oh, too bad. Too bad. All right, I'm going to close it. Yeah, guys, don't go too far, 2 minutes, and then I don't think we got much time left for today. So let's take a short break, and then we'll come back.
Example, when you assign it to 23, it'll be, no matter what you assign x as the precondition, it'll always be false because it'll just be reassigned.
Yeah, exactly. Exactly. That's why.
Thank you.
Take care.
I gotta watch the second half of the lecture.
Will do.
But thank you.
All right, guys, 1 more minute, and then we'll resume. Okay, we're got about less than 20 minutes for today.
Oh, actually, yeah, you sign up at the button.
So guys, quick question. Just in case we cannot finish everything next Thursday, just in case, do you guys prefer more about recorded lecture to be released beforehand, or you prefer more about a makeup lecture, maybe on the next day? That would be another possibility, I know, but let's...
We have optional learning, like if you want to learn it, you can watch the video. And then don't learn it.
Yeah, well, you know, because that's... Okay, well, we'll see how that goes. We'll see how that goes.
The biology of learning makes you require a little bit of a gap for the long-term evidence.
Yeah, I know, but, you know, so next Thursday before your exam, it's about a week, right? Yeah. Well, so I think we can finish a good part today. I think what's going to be left next week will be about the loops. Yeah, we'll see how I can do next Thursday. Yeah, and then.
Maybe we could just not ask them questions. Like ask them to save for the end of the lecture. We'll save the questions for the end of the lecture.
What do you mean save for the end of the lecture?
For the material if you want.
Sorry, say that again?
We could save the questions for the end.
Save the question for the end? What do you mean save the question?
Our question till the end of the lecture.
Well, yeah, we're gonna cover this. We're gonna cover this. Yeah. Anyway, we'll see. Okay, let's resume. Let's see how much you can do. Well, we'll finish in time. Okay, so let's say this. So we talk about variable assignments. Let's talk about 2 more, and then we'll do examples. The next one will be over here. So let's say the implementation now is somehow more complicated in the following sense. So we have basically, we still got some post-condition, but now the implementation is we can either go for S1 or S2, where S1 and S2 are simply some arbitrarily complicated implementation. Right? We kind of see this before when we do LTL. Okay? S1 will be branch 1 implementation. And S2 will be branch 2 implementation. And of course, this one tells us which branch we'll go. All right? What would be the WP rule? That's okay. I'm going to help you, most of you. Because we know we can either go for branch 1, in which case what we really want to establish the R by is S1. So we can calculate what's the WP for S1 to establish R. That's one WP we have to calculate, right? And for branch number 2, we can also go to S2, in which case we go for R. right? Either way, right? But this is like a two Boolean predicates. Somehow we want to contextualize them and combine them together. What do I mean contextualize them? When do we need this particular WP? We only need it when we actually go for this branch. When do we go to this branch? When B is true, right? Okay, so that's why we had to say, when B is true, that means we only care about this WP. If B is not true, we don't care about this. That's the nature of implication. On the other hand, we can say if not B is true, in that case, we care about this. Otherwise, if not B is not true, that means B is true, then we care about this. Now, again, we got two predicates. How do we combine them? Conjunction or disjunction? Disjunction? And or, basically. I think for, it turns out it should be conjunction, because in order to establish the postcondition, both branches must be able to establish that. You cannot say only branch 1 should be able to establish it, or branch 2. Both branches should. Okay? Both branches should be able to establish the postcondition by the corresponding statements, either S1 or S2. All right, hopefully it's not too bad, right? Okay, that's the rule. Okay, and one more follow-up. Okay, let's say we got this. Okay, let me put it aside over here. Let's say this is the Hoare triple I got. I got Q, and then I got R over here. And what I got is, let me put it here, is a if B, then S1. Otherwise, S2. Let me just omit the then just for now. Okay? Now, how do I turn this into the corresponding predicate? Yeah, again, we got to do Q implies.
So we don't get confused.
Yeah, so this part over here should be the WP, right? This part here, let me just put it down, should be the WP for this particular implementation to establish R. And what should that be? Exactly over here. Yes, I'm going to write it down. B implies WP for S1 to establish R. And the other branch as well. Now B implies WP for S2 to establish R. So two things we'll talk about. One is how to calculate the WP, which will give you this. The other one is higher level. Given this particular implementation and its specification, what will be the predicate to really prove its theorem in order to justify it? Okay, so that's one. Okay, good. Okay, that's it. Let's do one very quick example. Okay, so this one here, is this program really correct? Okay, I would suggest I'll do the very first step together with you, and you guys can try it. And then this is a solution on the slide. Is this program correct? What should we do? What we want to do is, okay, let's say this. If I may, just for now, for illustration purpose, this is, let's say, Boolean, B, and this guy over here is S1. And this guy over here is S2. So the Hoare triple we have, step number 1. Formulates the Hoare triple, which is going to be, this is a precondition, right? And y larger than 0. And then we have if B, then S1. Otherwise, S2, which is over here. And then I'm going to get bigger, larger than or equal to smaller. Okay, that'll be the first step. Step number 2. Calculate the WP for this to establish this. To establish bigger, greater than or equal to smaller. Okay, that's what you want to calculate. And this part here, give a try, and then you can check on the slides. Exercise. However, you wouldn't be able to calculate it completely because we haven't talked about how you can do this, which we will. We still have about 10 minutes for today. We can do a sequential composition. We'll do that. Let me mention about step number 3 as well. For step number 3, whatever WP you calculate, you're going to argue whether or not this particular existing precondition, which is x larger than 0 and y larger than 0. And that one implies the WP we calculate over here, is it a theorem? If it is, the original program is correct. Otherwise, it's not correct. Right? That's a picture you want to get. Right? And let's talk about how we can do sequential composition right now. Okay. Guys, any question before I move on? Now, before next Thursday, think about all these issues. I think these are the more tricky part we want to get right. Yes? Well, depending on what the WP is. Basically, once you get the implication, you want to prove it. I would say sometimes it will be quite obvious about whether it should be a theorem or not. You can just justify quickly. If it does not, give some counterexample. That's what I meant. Proof or disproof.
And for more complicated ones, are you going to teach us how to prove them?
Yeah, we'll see some equational style. Yes, we're going to see that. Okay. Okay, for that one, let's look at the final one. Okay, this will be the exercise, but before that, let's now look at the rule. Okay. Okay, that's something we just covered. And that's something you can compare your solution later. Okay, final rule, sequential composition. Okay. And this one here, let me put over here. Okay. Let's say this. What's the WP for some statements S1 followed by statement S2? R. Okay, think about this is more like a phase number 1. And think about this part here is like a remaining phases for your algorithm. Okay, now how do we define a rule? Yes?
I would guess you probably put it into different verticals, right?
No, simpler than that. I'll give you guys some visual hints. Let's take a look. The way to think about it is, let's say S1 and S2, right? The way to execute your program is going to be S1 followed by S2. Let's talk about 3 states over here. This will be the states right before S1. This will be the intermediate states after executing S1 but before executing S2. And this will be the states after executing S2. What we really want is R to be satisfied at this stage. Don't you agree? Let's go backwards. In order for S2 to establish R, what should be this starting intermediate states? WP for S2 to establish R. Do you guys agree? And now, in order for S1 to establish this WP, which itself is like a postcondition, what should be this one here? WP for S1 to establish this guy over here, which is the WP for S2 R. So simpler than you thought, right? Mm-hmm. Sorry, say it again.
I was going to say the precondition of the second one has actually postcondition.
Yes, yeah, that's kind of what was really visually suggested. Right, guys, let me say it again. Okay, the rule is not too difficult, but you most likely will put it on your data sheets anyway, but it's good to understand it, okay? Think about between these two phases, we got some intermediate states, beginning and the end. We go backwards. The final state should really satisfy R. That's our starting point, okay? In order for S2 to be executed and end up with R, we must make sure the starting point should be the weakest precondition for S2 to establish R. And then in order for S1 to reach in this intermediate states, that's the weakest precondition for S2 to establish R, you have to make sure you calculate another WP accordingly. All right? Think about this intuition. Okay? We got 4 minutes. Why don't we say we do this example together quickly? Okay? I'll give you guys just a few 30 seconds to look at what's really here. Given this particular Hoare triple, right, we want to know whether or not it is correct. Let's anticipate what should be the result. What is this doing? Swapping two variables, right? We want to swap the value between x and y. Okay, we are saying that given anything, if we try to swap x and y, we want to make sure after the swap, x is larger than y. Intuitively, is that correct? It would be correct if y is actually larger than x before the swap, right? Agree? That's our intuition. Let's see if that will work. Okay, let's do this a little bit. Okay, I'll do just enough so you can still see the big picture. Step number 1. We already got a Hoare triple. Calculate WP, okay? So I would say WP for this guy over here. The temp x, y, temp. I'll help you a little bit on calculating this, and then you guys can continue. Okay, how do we see that? Remember I mentioned before, phase number 1, and also, I really meant to say phase number 1. Beg your pardon. Phase number 1. Phase number 1 and the remaining phase. So think about this guy here is the phase number 1. And here is the remaining phase. It's like a S1 and S2. Okay? Let's now calculate the first step. So now, by the WP rule for sequential composition, we're going to get, what would that be? We're going to calculate this one first, right? It's going to be the WP for x, y temp to establish x larger than y. This is like this particular state. Okay, and then we want to make sure this will be able to establish that. In that way, we're going to put another WP for temp x. Oh, sorry, didn't align well. Are we okay with the very first step? No, that's it.
On the last slide, wasn't there like another part
No.
to it?
No, that's it. This one. That's the whole thing. Yeah, that's okay. Guys, are we okay with this? Okay. I'm going to also finish this maybe on Thursday, but you don't really want to wait for me for a week. You can definitely continue. Okay? I can do one more step. How about that? If you guys don't mind. Okay, now we can simplify this here. This will be phase number 1. Oh, sorry. This will be phase number 1. This will be phase number 2. Okay, so this part here stay the same. Okay, but for this one here, let me simplify just for this part here. It's going to be these two, right? So it's going to be the WP for Y temp to establish X larger than Y. And also we got this and also need to for XY to actually establish this, right? So that one there should be the WP for X assigned Y to establish. And don't forget, we also got this guy here. WP for temp assign X. That's the final thing. So we got this, this, and this. Do you mind if I take just 1 more minute or 2? Okay, why don't we just finish this, okay? Now, how do we simplify this? Well, it's actually by the assignment rule, right? WP rule of assignments. So we're going to replace the X, every occurrence of Y by temp. Okay? So I'm going to copy the blue part, the same. And the orange part also doesn't change. And finally, this part here is going to be Y will be replaced by temp. So that means X larger than temp. Okay? And what's the next one? And we're going to do this one here, right? WP rule of assignment 1, assignment rule for the second time. Now, this one I'm going to replace every occurrence of X by Y. So that one there is going to be WP, and then temp assigned to X, and then over here it's going to be Y larger than temp. Right, you can see X is going to be replaced by Y. Finally. So running out of space, if you don't mind, put it here. And then equals rule, WP rule of assignments. And this one here is going to be every occurrence of temp is going to be replaced by X. Okay? So what we got finally is Y larger than X. This will be the weakest precondition. And does it make sense? That one's telling you what you want to do is to swap X and Y. You want to establish X larger than Y. What will be the weakest precondition if Y is larger than X? Okay? And now, step number 1 is done. Step number 2. Okay, before we can go home, can anybody tell me what's the final step? What should we argue? The existing precondition over here, does it imply Y larger than X? Not really, right? No, okay, this one here. First of all, we can simplify this. This is the identity of implication. This is equivalent to just Y larger than X. This is not a theorem. We don't know. Because I can easily give you something that's going, okay. What you want to argue for this one here is not a theorem. Counter example. For example, what about X is something and Y is something? Just give me something that's not Y larger than X. Yeah, exactly, right? You can see here, what if X is 2 and Y is 1? In which case, it doesn't satisfy this. Okay? If you have, for example, X being 2 and Y being 1, in that case, you swap the 2. So that'll become 1 and 2. In that way, do you have 1 larger than 2 over here? Not really. So it doesn't always work. Okay, recap. I know, I really appreciate your patience. Recap. So we can continue next time. Whenever you're given a program over here, don't forget step number 1, calculate the WP, which we showed to you over here. And then we're going to argue whatever weakest precondition you calculate here is actually implied by your actual precondition. If it is implied, then you prove it. Otherwise, give some counterexample over here to show that it does not imply. Any question? Okay, I think this will be a very nice break point. Before next Thursday, do try to digest all the materials over here. And then the next topic will be how we can define correctness for loops. Yes, come over. Okay, thank you. I'll see you on Tuesday, I think.